Okay.
All right. Thanks, everyone. Welcome to today's coaching seminar. It's my pleasure to introduce Yutong Duan from UIC, and she'll talk about mall theory and the Lotka-Volterra system.
Thank you, Ronnie, and thanks for inviting me. So this is a model theoretic talk in differential closed field of characteristics 0 about the Lotka-Volterra system wheeled as a definable set. And this talk corresponds to two papers. The first is a joint work with Ronnie, and the second is a joint work with Corinne Eccles and Leo Jimenez. So the Lotka-Volterra system models predator-prey dynamics in an environment. Say X denote the quantity of prey and the Y denote the quantity of predator. Then the prey grow at a per capita rate N2 and the predator die at a per capita rate N4. When the two groups meet, the predation arises. Thus, the interaction term depends both on X and Y. But in this talk, I may generalize all the parameters to non-zero complex number and denote this system as LV ABCD 0. One immediate question and a central question for algebraic differential equation is what is the solution to the Lotka-Volterra system, and what are its elementary solutions or Liouvillean solutions? An elementary solution is like the functions we learned in calculus, for example, trigonometric functions, exponential functions, algebraic functions. And Liouvillean solutions can be defined in the following. First, let's say we start from C joint T, and a field L is a Liouvillean extension of C joint T if it's finally generated, and at each step I, either Fi is in the algebraic closure of previous step, or the derivative of Fi is in the preceding step, or the log derivative of Fi is in the preceding step. So the last two conditions means either Fi is an integral of some function, or e to Fi is an integral of some function. And we define a Liouvillean solution to an ordinary differential equation to be a solution in a Liouvillean extension. Thus, back to the Lotka-Volterra system, there are a lot of attempts to find Liouvillean solutions. For example, a quick search on Google Scholar gave a bunch of papers with high citations. And our study from this paper of Lotka-Volterra system are all under some specific parameters. For an example, when B equals to D, this scariform is a Liouvillean solution. Depending on alpha, changing of alpha and beta, which are all complex numbers, this is in fact a general solution. So thus, the next question to ask is, can one write out the general solutions for all parameters? And can we characterize when the general solution is Liouvillean or elementary or algebraic? Model theory has an answer to that. It says, if an ordinary differential equation of order greater than 1 is strongly minimal, then one cannot. To build up the connection between strong minimality and terms in like Liouvillean solution, let me introduce some history first. So it's around early 20th century, 1895 to 1905, Hanway and his students, Gambier and Fuchs, isolated six equations in search of new function. The solutions to these six equations satisfies Hanway property. Roughly speaking, the solutions can extend to meromorphic functions globally. And Penaway believed that the solutions of the equations, at least for general values of the parameters, defined new special functions. He gave a definition of non-functions and claimed to have proved that no solution of the first Penaway equation is null. And these are the 6 Penaway equations, except the first one. In fact, they are family of equations since there are parameters, and all these parameters are complex numbers. Yeah. So, but later, Liouville pointed out some flaws in his paper, and there were many attempts to fix results of Penaway. But it took a quite long time, and then the results are eventually corrected entirely by what we usually called Japanese school at 1980s or 1990s. It took the work of Nishioka, Okamata, Umamura, etc. to clarify his notion of irreducibility. Since people weren't so formal back then, what they exactly did they mean by non-function is like certainly Liouville would have counted, but they mean something even more general, which allows arbitrary functions that satisfy an order 1 solution, order 1 equation for an example. The terms, which is certainly stronger than anything they would have written, is the right notion. And Japanese, like Umamura and Nishioka, formalized this as irreducibility. And they also proved it for Penaway 1 to Penaway 6, except special values of the complex parameters. So it's not entirely clear in Japanese school that these equations are strongly minimal. Ronnie and Pele pointed out that the notion of irreducibility is equivalent to strong minimality in model theory later, and they proved generic Penaway equations are strongly minimal, geometry trivial, and omega categorical. These are all concepts in model theory, but they all have concrete incarnation in DCF0, which I will explain later. Also, this corresponds to Trinstan's results. So strictly disintegrated here just mean if you pick any n solutions from any of these systems, any of these family of equations, then the Trinstan's results of solutions and their derivatives reach the maximality over Cdrin T. They also studied rational transformations, taking one solution and its derivative to another solution of a different equation of different parameter. This rational transformation is called background transformation for Penaway 2 equation. For example, these 3 transformations on the slides, SC, T plus C, T minus C, since P2 alpha to P2 minus negative alpha, P2 alpha plus 1, and P2 alpha minus 1 respectively, and is for all the parameters. But whether they are only rational functions taking solutions and its derivative to solutions under a different parameter, the paper in which the best result that has been proved is this of Ronnie and James. So for instance, when alpha is a transcendental, then P2 alpha is non-orthogonal to P2 beta if they different by an integer. When that happens, the non-orthogonality is in fact witnessed by the 3 background transformation. But still there are some open questions. For example, when alpha are rational numbers, whether there are just these three background transformation, and also whether P2 3/4 is non-orthogonal to P2 4/5 is still an open question, since these two numbers are rational and they are now differed by an integer. So follow this literature, I may ask the third question. Is there any algebraic dependence of solutions in Lotka-Volterra system? And can one express solution of one system in terms of another solution to another system? Model theory again have an answer using strictly disintegrateness and orthogonality. And the answer again is no, if they have these properties. Thus, these are three main theorems I'm going to talk about today. Let K be a differential field extension of complex number, and let XY be a non-degenerate and non-constant solution to the Lotka-Volterra system.
Wow.
With thank you, with B not equals to D, then the transcendence degree of XY over K is either 2 or 0. And if we take n distinct non-constant and non-degenerate solutions, then again the transcendence degree reaches the maximality. If we take m distinct solutions to m systems respectively with different parameters, and then the transcendence degree again reaches the maximality. So let me introduce the language and theory first. Say FD is a differential field. If F is a field of characteristic 0 and is closed under taking derivative, where D denotes the derivation that satisfies the linearity and the Leibniz rule. We also assume all the fields in this talk are of characteristic 0. For an example, CT dt is a differential field, and and we define the field of constants to be the set of X that has derivative equals to 0, and we say a differential closed field is when F is algebraically closed and satisfy this existential closeness. We focus on a planar system today. That is x prime equals p xy, y prime equals q xy, where p and q are over constants. One can associate a derivation to the system ds and is on a rational function field. Say g is in variable xy over a different field k, then one can apply ds to g. And just this GD is the derivative with respect to the parameter. Okay. Thus, we define a complex invariant polynomial to be a polynomial in xy over constants, such that df equals to fg, where g is also over constants. And we say f is an invariant polynomial if f and g are over some different field extension k. An invariant curve is thus the zero locus of an invariant polynomial, and is in particular a rational first integral is a complex give a invariant polynomial. We'll also assume work in a sufficiently saturated model of DCF0, denoted as U delta, and assume the constant is C. Is the complex number. In model theory, a definable set is strongly minimal if all its definable subsets are either finite or cofinite, and it could be defined over any parameters. But we use an equivalent definition, and it's a valid definition in this talk. An algebraic differential equation is strongly minimal if there's no invariant curves or any differential field extension. The right-hand side is also called condition J. It's derived by Umamura. So, for example, if an ordinary differential equation is strongly minimal, then let P of x, y equals to 0 be an invariant curve over K, then there's a solution, and in fact, for any solution x, y, the transcendence degree of x, y over K is 1. And strong minimality of an equation of order greater than or equal to 2 implies it has no Liouvillein solution, because each step of Liouvillein extension is either 0 or 1. Since we had some Liouvillein solution to the Lotka-Volterra system when it has b equals to d, thus it must have invariant curve. So for b equals to d and for arbitrary a and c, Lotka-Volterra system has invariant curves xy equals to 0, cx minus ay equals to 0, cx minus ay minus z equals to 0, where z satisfies this order 1 differential equation. One can prove this just by calculation. And especially, we show that these are all the invariant curves of the Lotka-Volterra system when b equals to d. To summarize a bit about the Lotka-Volterra system, for all parameters, there are only two constant solutions, and xy equals 0 is an invariant curve for all parameters. There are also some transformation between systems. By sending x to cx and y to ay, there's a bijection sending LV ABCD 0 to LV 1B1D 0. Thus, we can reduce all the discussion by assuming A equals to C equals to 1. And furthermore, when B equals to D, the system is symmetric. Thus, one can swap x and y to get another transformation. Thus, we define the non-degenerate LV system to be the Lotka-Volterra system without the invariant curve xy equals to 0. And now I'm going to prove the strong minimality result. So firstly, Ronnie and I prove it when B and D are Q-linearly independent. The proof relies on the bound of non-minimality degree, which I will explain later, and the pizza series technique. So we start by assuming it's not strong minimal and denote this courtesy for this finite generated constant field over Q. Then there exists a differential field K and a solution UV such that the transcendence degree of UV over K equals to 1. This K and UV are the witness of non-strong minimality. Now I'm going to use pizza series technique. So let K be a differential field, and the field of formal pizza series can be seen as union of a formal Lorentz series with fraction exponent. And when we know that when K is algebraically closed, then the formal pizza series is also algebraically closed. And since the transcendence degree of UV over K is 1, thus U is in KL joint VL, and we can apply the algebraic closeness of the pizza series. Thus, we can write U as a pizza series expansion in V as 0 And if one takes the derivative of this pizza series, then one gets another series for U prime. One can also calculate the differential equation for U from the system and can plug in these two series into the equation. Thus, one gets an equation for series. By the transistance of V over K, one can compare the coefficient of degree terms. And in this case, we compare the lowest degree term, which gives us a generic solution to this order 1 differential equation, A0 prime equals to MA0 in K ouch. Notice there's no issue here, since K can be arbitrary, but by a theorem by Freitag, Joy, and Musa, which says the non-minimity degree of the equation must be less than or equals to 1. So what does the non-minimity degree mean? By a model theory principle called stable embeddedness, a forking extension of a type can be witnessed by realizations in the type. And forking has a concrete incarnation here. It just means the drop of transistance degree. Thus, the assuming non-minimity and what we were doing is like witnessing the forking extension. And the non-minimity degree is defined to be the least number of realizations that witness this forking extension. Since it's less than equals to 1, we can in fact choose the K to be this curly C joint XY ouch. Thus, we have another polynomial relation again, and one can apply the pizza series technique again. And it is at this step we use the condition B and D are Q-linearly independent. And at last, we reach a contradiction. Notice at the first step, we didn't use any assumption, and also there's no generic solution to A prime equals to MA in complex number. So there's no complex invariant curve for Lotka-Volterra system as a corollary. Now let me go further to question 3. So in model theory, we say a strongly minimal set we say X is geometrically trivial if for any element A in X and the subset B in X, if A is in algebraic closure in the model theory sense of B, then there exists an element little b in B such that A is in the algebraic closure of B. But again, there's a better, again, a good thing happened here is that there's a equivalent definition for geometric triviality in DCF0. It says when there's a algebraic relation between any n solutions and all its derivatives, then there must be an algebraic relation between two solutions and their derivatives. So geometric triviality is a concept comes from people trying to characterize strong minimality in model theory, and there is a deep theorem called trichotomy theorem. I may not introduce it today, but basically saying either the strong minimal set is field-like or group-like or geometrically trivial. And there's a fact saying that a strong minimal defined set over constant is automatically geometrically trivial. Thus, we can apply to Lotka-Volterra system, and thus to show the algebraic independence of any n solutions of Lotka-Volterra system now reduced to show the algebraic dependence of any two solutions. So there is a sketch of proof. Assume x, y, and uv are two solutions to the system, and let z denote x minus y and w to be u minus v. Then z and w satisfy this following equation. This equation satisfies a special form. On the left-hand side is a derivative of a differential polynomial, and then on the right-hand side is sum of log derivative of differential polynomials. And we call this as Bristowski's form. And there's a theorem from Bristowski says that, let me call this equation S. So if S is strongly minimal and of order 2, and if ZW are two solutions to S, if there is a polynomial relation of Z and W, then one can reduce the relation to this form, f of Z equals to E times f of W plus F, where E and F are constants. So we can apply this theorem directly to the Lotka-Volterra system, which give us Z equals to EW plus F, since we have very simple form on the left-hand side of the equation. And this is a linear relation, which is very easy to rule out. Thus, one can reach a contradiction. So after Ronnie and I proved the case B are Q-linear independent from D, we are inspired by Remy for another approach to all the cases. So notice we already proved that there are no complex invariant curves. Another fact from Remy says that if S is a system of order greater than or equals to 2 and is over constant, and there is a singular point X that is not content in any complex invariant algebraic curve, then the generic type of the system admits no almost proper fibration. And we proved that a planar system is strongly minimal if and only if it has no almost proper fibrations. Thus, finish the proof. In fact, this theorem can generalize to systems over constant that has higher orders, and with a proper concept of minimality. Since the way we proved we use the Bristowski form, and the theorem of Bristowski doesn't depend on B and D, thus we can apply the way to prove all the algebraic independence for all the parameters. We can also generalize approach to other Lotka-Volterra system. We generalize the second equation from cxy plus dy to cxy plus dy squared here. So the second equation is a homogeneous equation. And again, xy equals 0 is a complex invariant curve. So we include the inequality here. And this Lotka-Volterra system, again, has a singularity and has no Liouvillean first integral. And in fact, In the paper with Ronnie, we showed, again using Pfister's technique, that there are no complex invariant curve of this 2D Lotka-Volterra system, because this 2D things it still have two dimension. It still have two variables. And as a corollary from the previous approach, it is strong minimal automatically and is for all parameters. After we prove the strictly disintegrateness, that is algebraic independence of any n solutions, Ronnie asked me whether there's a way to generalize Briggs-Stokes theorem. And here it is. So given two equations of Briggs-Stokes form and take two solutions respectively, if there are any algebraic dependence, then it still can be restricted to F1 A1 equals to E times F2 A2 plus F. Notice changing the variables doesn't change the left-hand side of the equation, which is interdefinable with the Lotka-Volterra system. Thus, we still can get a linear relation between solutions, which again is possible to rule out. And thus, we proved the orthogonality between any two systems. And by some forking argument or calculation on the transitance degree, one can in fact prove this more general theorem, saying if we have any n systems of different parameters, all have bi not equals to di, and just take m solutions from these systems, then the transitance degree reach the maximality. Since we still have some time, let me have some words about this theorem with Leo and Christine. So
Yutong, do you maybe want to say what no proper vibration means?
Yes. So if we have two types, P and Q, assume P and Q are stationary types. That is, they all have one unique non-forking extension. Then a proper vibration F is a diagonal map from P to Q, such that the fiber is not algebraic, and also Q is not an algebraic type. So we first apply a fact by Musa, that is a classification of no proper vibration. It says either P is minimal or P is almost internal to a generic type of the constants if working in DCF0. So in particular, the second case implies it is non-orthogonal to the constants. Then there's a theorem by Christine and Liu, says if it's non-orthogonal to the constants, then there must exist this invariant polynomial over some differential field, such that DSG equals gamma G, and DSG, or DSG equals gamma for some gamma in the differential field. And this G in particular satisfies an order 1 differential equation. Since we assume K is strictly greater than 1, thus this G itself witnesses a proper vibration, and this is a contradiction. Therefore, P must be minimal. And that is all for my presentation for today. Thank you.
Thank you, Yutong. Do we have any question for Yutong? seems like we have no question. So maybe I'll ask one. So you haven't proved that the independence result for the 2D Lotka-Volterra yet. Any idea how you could do that?
Since we haven't shown it has the Bristol's form, so far there's not a clear clue for that. So it could be a hard task, and if I can prove that, it may shed some light.
Okay, I might have a just non-expert question. You mentioned somewhere that a certain thing is open that involve two fractions, 3/4 and 4/5. Where those two numbers come from?
Or just randomly choose these two numbers because they are
Oh,
right.
okay.
Yeah.
Okay. All right.